Welcome to the debate. Today, we are diving into one of the most foundational, yet, let's be honest, fiercely debated elements of classic object oriented design, the singleton pattern. It came from the original Gang of Four patterns, and, well, the singleton, defined by restricting instantiation to just one single instance and providing global access, it stands today as maybe the most contentious construct in software architecture. So, our central disagreement really boils down to this. Is the classic implementation of the singleton pattern still a valid solution, for efficiently managing those unique system resources, things like connection pools or configuration managers? Or have its architectural downsides frankly forced its definitive classification into the anti-pattern category? This tension, it comes from the pattern's powerful intent versus the pretty profound structural trade-offs that come with its specific implementation. I'll be defending the practical necessity, the inherent resource efficiency that comes from the singleton intent, while my counterpart here argues that the pattern's deep violation of core design principles and, crucially, its devastating impact on testability render the traditional implementation obsolete.
Yeah, and I think that's the crux of it. I believe the architectural cost of the classic singleton vastly outweighs any, let's call it, superficial convenience it offers. My core position is that this pattern is, well, it's functionally equivalent to a global variable, just maybe in disguise. And that global state, it immediately introduces architectural rigidity and, frankly, long-term technical debt that modern systems just can't tolerate. We can start right with the principles. The pattern fundamentally violates the single responsibility principle, and it does so pretty egregiously. The class that's made to handle its core business logic, like say your configuration manager example, is simultaneously burdened with this incredibly complex, often low-level task of managing its own lifecycle. I mean, this is where you see developers wrestling with intricate concurrency stuff, like Python metaclasses or explicit threading lock mechanisms, or even attempting complex double-checked locking, all just to try and ensure thread safety. That overhead, it has nothing to do with actually managing configuration settings. And furthermore, the classic singleton, it introduces tight coupling through what are essentially hidden dependencies. When a high-level component, maybe a user service, internally calls configuration manager.getInstance, it never explicitly declares that dependency anywhere. It's just this silent, mandatory relationship that honestly cripples maintenance and makes the code much harder to reason about.
Okay, but I think your focus is maybe too heavily skewed toward the implementation flaws. It feels like it overlooks the genuine, immutable architectural problem the pattern was actually designed to solve in the first place. The singleton pattern exists because some components are intrinsically singular. I mean, a system can really only have one authoritative instance of a central logging facility, right? Or maybe one instance representing the operating system's resource allocation manager. There are things that are just one. And by enforcing this principle of unity, we communicate clear design intent. We prevent potentially catastrophic issues that can arise when multiple instances of some resource-intensive component are accidentally created. Take, for example, a high-volume database connection pool. Guaranteeing it's created only once provides tangible resource efficiency. It conserves both memory and CPU cycles that would otherwise be completely wasted on redundant initializations. It also ensures centralized control, meaning all parts of the application access the single authoritative source, which is pretty critical for maintaining data consistency across the entire system.
Right. The intent to have a unique resource, I don't think anyone argues with that. The problem is the mechanism you use to access it. You just said the singleton provides global access. And that right there, that's the core architectural flaw we're talking about. I mean, consider the dependency inversion principle, right? Which states that high-level modules shouldn't depend on low-level concrete details. When your user service just reaches out and grabs that configuration manager using some static accessor, getInstance, or whatever, it is tightly bound to that specific concrete class. You've basically introduced a hard-coded dependency hidden deep inside the user service implementation details. And this makes the user service practically impossible to decouple, or test, or substitute independently of the actual concrete configuration manager.
But this focus on achieving, let's say, perfect inversion Doesn't that lead to a practical maintenance nightmare sometimes? Especially for components that are truly ubiquitous, used all over the application. Think about a logging service. If it's needed by, say, 90% of your classes, insisting on constructor injection means you have to pass that logging instance through potentially dozens of intermediate object layers. It becomes this tedious chore, often called plumbing. The resulting code gets bloated with constructor arguments that have nothing to do with the class's primary job. They're just there to facilitate resource delivery. Global access, for those few specific resources where uniqueness is an immutable system-wide constraint, well, it offers a certain simplicity that genuinely can boost early development speed.
Sure, convenience, but that convenience buys you immediate speed at the cost of crippling future flexibility. That rigidity you accept just to avoid some plumbing, it directly violates the open-close principle. The idea that, software entities should be open for extension but closed for modification. If, for instance, you need to extend your logging service later, maybe incorporate asynchronous queuing or move its persistence from a local disk to some cloud service, every single consumer of that singleton is tightly coupled to the concrete implementation through that static method call, getInstance. To change the behavior, you're forced to modify the original concrete singleton and potentially modify every single class that relies on its accessor, rather than just, introducing a new implementation via an interface or something similar. That's not just a little bit of debt. That's a severe impediment to refactoring and evolution down the road.
Hmm. I acknowledge that coupling is an issue, sure, but the rigidity argument often seems to assume that these unique resources are frequently changing their fundamental structure. A sensible logging mechanism, once it's defined, is generally pretty stable at the system level, wouldn't you say? It feels like the structural change is what introduces the complexity, not just the mere existence of a unique instance.
Okay, maybe for logging, sometimes. But the most pragmatic, honestly, the undeniable flaw of the classic implementation is the testability nightmare it creates. Unit testing requires testing a class in isolation, right? Replacing its collaborators with mocks or stubs. The singleton pattern aggressively resists this. Because that dependency is hidden away behind a static method, you cannot simply inject a mock configuration manager or a mock database connection pool into your user service for a test. Your unit test is forced to rely on the actual live stateful singleton, and relying on that immediately makes tests slow, unreliable. But the worst consequence really is state leakage, because that singleton instance persists across the entire test suite's execution. If test A modifies a setting in the singleton, let's say it switches debug mode to true, that altered state leaks into test B, test C, and test D, which might be expecting the default configuration. This means your tests become dependent on the order they run in, which is like the definition of unreliable, brittle automated testing. It's a disaster for CI/CD.
Yeah. Okay, that is a deeply compelling critique. And the problem of managing global mutable state in unit tests is absolutely where the traditional pattern implementation completely breaks down. I can see that. However, maybe look at it this way. The sheer complexity that's often required to implement a robust, thread-safe singleton. You mentioned the explicit locks, the volatile variables, the need for complex patterns like double-checked locking. That doesn't just reveal implementation difficulty. It kind of underscores that the resources being managed are inherently complex and unique, especially within a highly concurrent environment. The pattern, at its core, was designed to ensure resource integrity under contention. Now, while it fails spectacularly at testability, that robust, sometimes difficult implementation, it was arguably necessary at the time to solve a fundamental concurrency problem: how to manage shared stateful resources safely. We can manage that necessary complexity, but ideally without having the implementation details compromise the entire architectural structure like the classic singleton does.
And that brings us, directly to the modern solution, which isn't about patching the singleton, but really abandoning its self-managing implementation entirely in favor of dependency injection, or DI. DI allows us to separate those concerns really elegantly. We strip the configuration manager of its static accessor, all its lifecycle management logic, and we turn it into just a plain old Python object, or POPO, or whatever equivalent in your language, solely responsible for its actual job, the configuration logic. Then we use constructor injection. By explicitly requiring the configuration manager instance in the constructor of the user service, we satisfy the dependency inversion principle. The dependency becomes visible, explicit. The real benefit, though, is the immediate resolution of that testing problem we just talked about. So when we run a unit test against the user service, we simply instantiate a mock configuration manager that mimics the necessary interface, and we just pass that mock into the user service constructor. Boom. This simple act of refactoring proves, I think, that the classic patterns implementation was the root of the problem. We gain perfect test isolation, we eliminate the state leakage problem, and we completely remove that hidden coupling.
Okay, and this is where the debate, I think, moves from conflict towards synthesis. Because while I agree wholeheartedly that dependency injection resolves those implementation flaws, the hidden coupling, the poor testability, I would frame this outcome slightly differently. Dependency injection doesn't kill the singleton intent. I'd argue it actually validates the architectural need for a single shared resource. Think about DI frameworks, whether it's Spring, Geis, .NET's DI, whatever. They have dedicated concepts like singleton scope or singleton lifetime. These mechanisms allow the framework itself to take responsibility for ensuring that only one instance of that configuration manager is ever created. That responsibility is effectively delegated, often to what's called the composition root, the central place where objects are constructed and wired together at application startup. So we still have a single instance, shared globally, fulfilling the original intent. But now the object itself is clean, it adheres to the SRP, and it's easily testable because it's just a normal object, a POO. The complexity of managing uniqueness is moved externally. So we get the resource efficiency and the singularity we needed, but without compromising maintainability.
Exactly. And that's why the structural damage caused by the classic singleton implementation, that aggressive coupling, the introduction of harmful, persistent global state, mandates that the pattern as originally defined by the Gang of Four should be classified definitively as an anti-pattern today. It just forces us to violate SRP and creates these impossible testing scenarios. DI is simply the superior modern approach because it enforces architectural discipline. We can achieve the goal of having a unique instance while still adhering to fundamental principles like SRP, maintaining robust testability, and crucially, requiring dependencies to be explicit, which promotes that essential loose coupling we need for maintainable systems.
Yeah, I think this discussion clearly shows that the underlying need for resource control and singularity remains absolutely valid. The shift, driven primarily, as you pointed out, by the engineering necessity of automated reliable unit testing, it proves a key evolution in software design. We now prioritize long-term maintainability over that kind of superficial self-managing convenience. So the takeaway seems clear. While the architectural goal of a single instance is often necessary, the traditional implementation, where the class manages its own instance and exposes it globally, is, well, irreparably flawed for most modern uses. Modern systems embrace the singularity requirement, but delegate the responsibility for enforcing that uniqueness to the system infrastructure, like a DI container. And this resolves the conflict between robust system design and the efficient management of shared components. Of course, there's still more to explore, maybe edge cases where even DI might struggle with truly external constraints. But for day-to-day application architecture, the answer seems remarkably clean now.